Our final topic for this module on precalculus is trigonometry. Trigonometric functions are functions which relate angles in right-angled triangles to ratios of the side lengths in that same triangle. There are a bunch of different configurations for an angle and two sides to determine such a function. So for each configuration we have a different trigonometric function. Here are the three primary trigonometric functions. The first, sine, is the function which takes an angle in our right angle triangle and computes the ratio of the opposite side length divided by the length of the hypotenuse. Here we've used O to represent the length of the side that is opposite the angle theta, and we've used H for the length of the hypotenuse. Our second trig function is cosine, and it's written as cos. Cos takes an angle as input and computes the length of the adjacent side divided by the length of the hypotenuse. The third trig function is tangent, or tan, and it takes an angle to the ratio of the opposite side length divided by the adjacent. You can check that this is the same as sine over cosine. Lots of people will use the mnemonic SOHCAHTOA to help them remember that sine is the opposite over the hypotenuse, cos is the adjacent over the hypotenuse, and tan is the opposite over the adjacent. Let's start with a simple example. Here we've given a triangle with side lengths 3, 4, and 5, and we are told that one of the angles in this triangle is 37 degrees. With all this information, we can evaluate our trigonometric functions at 37 degrees. Sine of 37 degrees is the opposite side length over the hypotenuse, which is 3 over 5. Cos of 37 degrees is the adjacent side length over the length of the hypotenuse, or 4 over 5. And tan of 37 degrees is the opposite side length over the adjacent side length. That is 3 over 4. It's not normally so easy to evaluate our trig functions at a given angle. If you're given an angle, it's hard to determine the side lengths of the right-angled triangle that contain that angle. If you're given a right-angled triangle and its side lengths, it can be hard to find the angle. So really we need to see side lengths and angles at the same time. Before we move on, let's see what would happen if we were asked to evaluate our trig functions at 53 degrees. You can find this angle by remembering that the angles in our triangle should add up to 180. If we want to compute sine of 53 degrees, then we have to reinterpret what we mean by the opposite side. The side opposite of the angle 53 has length 4. The sine of 53 degrees is 4 over 5, so it's the same as cos of 37. Similarly, cos of 53 is the adjacent over the hypotenuse. The adjacent side now has length 3, so we get 3 over 5. This is the same as sine of 37. Finally, since the opposite and adjacent sides of this angle are flipped from the old one, tan of 53 degrees is 4 over 3. Let's move on. Now I'd like to talk about a question which might be nagging at you. Our trig functions take angles as inputs and produce as outputs certain ratios of side lengths. You might ask where this triangle comes from. Given an angle, there are a bunch of different right triangles which contain that angle but which have different side lengths. Which triangle is going to give us the correct ratio? The answer is that all of these different right triangles with a fixed angle will give the exact same ratio of sides. This comes from a fact about similar triangles. Two triangles are similar if they contain the same three interior angles. Here we've depicted two similar triangles, and we can mark which angle corresponds to which. When two triangles are similar, their side lengths are proportional. That means that if we write down the side lengths of the first triangle as A, B, and C, then the side lengths of the other triangle are obtained by scaling these values up by a constant. Let's call this constant k. So here I've labeled the sides of the second triangle as length r, s, and t. So r is k times a, s is k times b, and t is k times c. Thus the ratio of two side lengths, say r divided by s, equals k times a divided by k times b, which is just a over b. So the ratio of two side lengths in one triangle is the same as that same ratio of side lengths in the second triangle. This would not happen if the triangles did not have the same interior angles. The same happens for other ratios as well. If we turn our attention back to trig functions, when you're asked to compute the sine of an angle theta, we start with a right triangle and add the angle theta. Notice that the third angle is determined by this as 90 minus theta. Now any two triangles that we pick with these angles will be similar triangles. So we know that they have the exact same ratios of side lengths. So we know that sine of theta takes on just one single value. It doesn't depend on the choice of side lengths. Let's continue the thought from our previous slide, that once the angles inside a triangle are determined, it doesn't matter how large the triangle is. The ratios of its side lengths will always be the same. So if we were trying to evaluate sine or cos, it might be useful to pick one of the side lengths to make the calculation easier. A good choice is to make right-angled triangles which have their hypotenuse of length 1. If we set h equal to 1, then sine of theta is the length of the opposite side over the length of the hypotenuse, which is simply the length of the opposite side. Also, when h equals 1, cos of theta is the length of the adjacent side. So let's draw a right-angled triangle with a hypotenuse of length 1. Notice how this triangle fits into the unit circle, the circle with radius 1. If we label the angle at the origin theta, then this right triangle's height is sine theta, and its width is cos of theta. That places the upper right corner at the coordinate cos theta, sine theta. This works for any angle, and it gives us another way to define sine and cos. If we plot a point on the unit circle, and we measure the angle from that point down to the positive x-axis as theta, then the coordinates of the point are always cos theta, sine theta. Cos is the horizontal component, and sine is the vertical component. This geometry tells us that a point of the form cos theta sine theta must lie on the equation x squared plus y squared equals 1, which is the equation of the unit circle. So cos squared theta plus sine squared theta is equal to 1 for any angle theta. We're almost ready to start plotting the graphs of sine and cosine. But first I want to talk about how we measure angles. So far I've measured angles in degrees, but from now on we will be using radians. Radians are a straightforward conversion from degrees. If we have an angle in degrees, and we multiply it by 2 pi, and then divide it by 360, we will get the radian measure for that angle. So 360 degrees is 2 pi radians. 180 degrees is pi radians. 90 degrees is pi by 2 radians. 45 degrees is pi by 4 radians. And 30 degrees is pi by 6 radians. Whenever we put an angle into a trig function, we'll now assume that it is measured in radians. With this convention, let's plot sine and cosine. At 0 degrees from the x-axis, we get the point 1, 0 on the unit circle. Thus cos of 0 is the x-coordinate, cos of 0 is 1, and sine of 0 is the y-coordinate, sine of 0 is 0. At 90 degrees, or at pi by 2 radians from the axis, we have the point 0, 1 on the unit circle. So cos of pi by 2 is 0, and sine of pi by 2 is 1. Continuing in this way, we get more values for sine and cos, and so we can fill in the graph like so. The unit circle definition of sine and cos is allowing us to evaluate these functions at angles which don't really make sense for right triangles. For instance, if we go past a full revolution, if our angle is larger than 2 pi, then sine and cos begin to repeat. We say that they are periodic and that their period is 2 pi. Now that we know the overall shape of the graphs for sine and cosine, let's find some more exact values of points on these functions. Problem 31 asks us to find sine of pi by 4 and cos of pi by 4. Here we have a graph of the unit circle and an angle of pi by 4, which is 45 degrees, drawn from the x-axis. The point at the end of this radius is the point cos of pi by 4, sine of pi by 4. So we just have to find another way to compute the coordinates of this point to get cos and sine explicitly. Here's the trick. Let's draw a vertical line down from our point to the x-axis. This forms a right angle at the x-axis, and the top angle is pi by 4, since the angles have to add up to pi radians. Thinking in degrees, this is a triangle with 45, 45, and 90 degrees. Whenever you have two angles in a triangle that are equal, you have an isosceles triangle. That means that two of the side lengths are the same. So we can conclude here that the opposite and the adjacent sides of this triangle have the same length. Let's call that length A. The hypotenuse of this triangle has length 1, since the hypotenuse is the radius of the unit circle. By the Pythagorean theorem, we have that the length of the hypotenuse squared is equal to the sum of the squares of the other two side lengths. Thus, 1 squared is equal to a squared plus a squared, which is 2a squared. We can now solve for a by dividing by 2, so a squared is 1/2. We can take roots to get that a is equal to 1 over the square root of 2. And notice that we can ignore the negative square root when solving this because we know that a has to be positive. Finally, our point, cos of pi by 4, sine of pi by 4, is a distance of a over and a up from the origin. So it's at the coordinates a, a. Or in other words, 1 over square root of 2, 1 over square root of 2. That's it. We found that sine of pi by 4 and cos of pi by 4 are both equal to 1 over square root of 2. This is around 0.07 if you ever need an approximation, but I encourage you to memorize the exact value, or at least the process for finding it. Let's move on to our next problem, which asks us to find the exact values of sine of pi by 6 and cos of pi by 6. Again, the point on the unit circle, which is an angle of pi by 6 or 30 degrees from the x-axis, is the point cos of pi by 6, sine of pi by 6. So we just need to find the coordinates of this point. This time we'll drop a vertical line from our point past the x-axis down to the unit circle again. Notice that this takes us to the reflection of our original point in the x-axis. If we draw a line from the origin to this point, it's also the mirror image of the radius above. So it's also an angle of pi by 6 from the x-axis. We now have one large triangle with a total angle at the origin that is pi by 6 plus pi by 6, which is pi over 3, or 60 degrees. The other two angles are also pi by 3, since all the angles in the small triangle have to add up to pi radians. Since all the angles in the large triangle are pi by 3, the large triangle is an equilateral triangle, so all the side lengths are equal. We know that the two lines coming from the origin have to have length 1, since they go out to the unit circle. So this last side length must also have length 1, because the triangle is equilateral. Since the bottom segment of this last side is the mirror image of the top segment, they are of the same length. That means that both have length 1/2. We can now solve for the last side length of the small triangle in the first quadrant using the Pythagorean theorem. If we label it as a, then a squared plus 1/2 squared is equal to 1 squared. So a squared is equal to 1 minus 1/4, or 3/4. Thus a is equal to the square root of 3 over the square root of 4, which is just 2. This gives us the coordinate of our point as square root of 3 over 2, 1/2. So cos of pi by 6 is the square root of 3 over 2, and sine of pi by 6 is 1/2. You can also find sine of pi by 3 and cos of pi by 3 by using that same small triangle. Sine of pi by 3 is 1/2, and cos of pi by 3 is the square root of 3 over 2. Let's use the values that we found in these last two problems to find a whole bunch of points that are on our unit circle, and hence a list of other values for sine and cos. First, we can label all the points that are either on the x-axis or on the y-axis. These give us the values of sine and cos at any multiples of pi by 2, that is, any multiple of 90 degrees. Since cos of pi by 4 and sine of pi by 4 are both 1 over the square root of 2, on our diagram we have the point 1 over the square root of 2, 1 over the square root of 2 at the end of the arm at pi by 4. Due to symmetry, we can label the other points. Notice how the sign of the coordinates change as we move them into different quadrants. If we are left of the y-axis, then our x values are negative. That means that cos is negative to the left of the y-axis. Similarly, the y-coordinates are negative below the x-axis, so sine is negative in those quadrants. Our next circle shows points along the unit circle at angles that are multiples of pi by 6 radians, or 30 degrees. And we're skipping the angles that we've already seen. We know the point at angle pi by 6 is at the square root of 3 over 2, comma 1/2. And at pi by 3, we get the point 1 over 2, comma square root of 3 over 2. You can see that these two are reflections of each other in the line y equals x. If we take these 2 points and reflect them in the y-axis, we'll flip the sign of the x values. We can also recognize that those points will be at 2 pi by 3 and 5 pi by 6. Just measure how far they are from the y-axis to see that we have the angles right. Now we can reflect all 4 points that are above the x-axis down below the x-axis to get our last 4 points. This flips the sign of their y-coordinates. When you look at these two diagrams, you can find the values of cos by using the x-coordinates, and the values of sine by using the y-coordinates. For instance, sine of 7 pi by 6 is minus 1/2, and cos of 11 pi by 6 is the square root of 3 over 2. Our next problem is to graph 2 times the cos of pi by 2 times theta plus 1, and then all plus 1. You'll recognize that this function is obtained from cos by composing it with both a vertical and a horizontal transformation. Let's build up this formula step by step from y equals cos of theta. We start by replacing theta with pi by 2 times theta, which compresses the graph horizontally by a factor of pi by 2. So since the period of cos is 2 pi, our new period will be 2 pi divided by pi by 2, which works out to be 4. So we'll see a whole wave of cos between x equals 0 and x equals 4. Let's draw that graph. Next, I'd like to substitute in for theta plus 1. This shifts the graph to the left by 1 unit. So here's the graph of cos of pi by 2 times theta plus 1. To get the final equation, we first scale everything by a factor of 2, and then add 1. This stretches our graph vertically first, and then we shift it up by 1 unit. Before the stretch, our graph went up and down between y equals 1 and y equals minus 1. After the stretch, it goes up and down between y equals 2 and y equals minus 2, and then after shifting up by 1 unit, our graph oscillates between y equals 3 and y equals minus 1. So the central axis of our final graph is at y equals 1. In this problem, we're also asked to rewrite this function in terms of sine. Since our function starts at its central axis and then goes down, it looks a lot like negative sine. Its period is also 4, so the input should be pi by 2 times theta instead of just theta. Also, it has been stretched and shifted vertically, much like in the old equation. So in terms of sine, f of theta is equal to minus 2 times sine of pi by 2 theta. No horizontal shift is needed, and the vertical flip comes from that minus sign. There are many relationships between trigonometric functions which are useful for simplifying and manipulating equations. We call these relationships trigonometric identities. One of the most basic trigonometric identities is the rule that sine squared of an angle plus cos squared of that same angle is equal to 1 regardless of what the angle theta is. This identity comes from the unit circle. We know that a point cos theta comma sine theta is always on the unit circle, so these coordinates need to satisfy the equation of the circle, which is x squared plus y squared equals 1. So this gives cos squared plus sine squared equal to 1. Let's find some more identities. Problem 35 suggests that tan is sine over cosine. To prove this identity, we can draw a right-angled triangle and use SOHCAHTOA. We know that sine of theta is the opposite over the hypotenuse, and cos of theta is the adjacent over the hypotenuse. So sine over cos is the opposite over the hypotenuse, all divided by the adjacent over the hypotenuse, and multiplying by h over h, just multiplying by 1, shows that this is equal to the opposite over the adjacent, which is tan of theta. That proves our identity. When we prove an identity from the rules that we already know, we say that we have derived it. Deriving is different from differentiation, which is a specific process that you learn in calculus. Moving on, I'd like to define three new trigonometric functions in terms of sine, cosine, and tan. The function called secant, written SEC, is the reciprocal of cosine. Cosecant, written CSC, is the reciprocal of sine. This can be a little confusing since the co prefix disappears, but these names have been set by a long history. Finally, cotangent is the reciprocal of tangent. If you were to write out a right-angled triangle which contained the angle theta, you could write these trig functions in terms of the side lengths. They come from flipping the ratios that you know from SOHCAHTOA. Let's prove the next identity. We want to show that tan squared of theta plus 1 is equal to secant squared of theta. This looks a lot like the identity sine squared theta plus cos squared theta is equal to 1. So let's start with that identity and manipulate it to get the one that we want. We know that tan is sine over cosine, so let's divide the equation by a cosine squared theta to get sine squared over cos squared, which is tan squared. This also cancels with the cos squared to give 1. On the right-hand side, we are left with 1 over cos squared theta, and 1 over cos is secant, so we get the desired identity. Problem 37 is much more open-ended than our previous problems. It asks us to write down a list of identities that come from transformations and similarities between sine and cosine. Here we have a picture of sine and cosine. Keep in mind that these functions go on infinitely in both directions, repeating the same shape in every 2 pi period. Let's see if we can find some symmetries. The easiest one to see is in cosine. If you flip cosine horizontally, that is, if you reflect it in the y-axis, you'll get back to the original graph. Because of the symmetry about the y-axis, cosine of any angle theta is equal to cosine of the negative of that angle. A horizontal reflection doesn't change the graph. If we reflect sine horizontally, it's the same as reflecting sine vertically. You'll notice that both the horizontal and the vertical reflections of sine pass through the origin, and at pi by 2 they both have height minus 1. So sine of minus theta, the horizontal reflection, is equal to minus sine of theta, the vertical reflection. We can also translate both of our graphs horizontally by 2 pi, and they won't change. This works in the opposite direction as well, and can be repeated over and over. So sine of theta is sine of theta plus 2 pi, and it's also equal to sine of theta plus k times 2 pi, where k is any integer. Also, cos of theta is equal to cos of theta plus 2 pi, which is equal to cos of theta plus any integer multiple of 2 pi. These identities tell us that sine and cosine are 2 pi periodic. The last thing that we can do is we can transform sine into cosine and vice versa by a horizontal shift. For instance, if we move sine to the left by pi by 2, we get to cosine. So cos of theta is sine of theta plus pi by 2. We are adding here to shift the graph to the left. This can also be done in reverse. If we move cosine to the right by pi by 2, then we get to sine. So sine of theta is cos of theta minus pi by 2. Take some time to look at cosine and sine and see if you can find any other identities. The identities that you're likely to find come from applying combinations of the ones above. We now come to our final 2 problems on trigonometry. In these problems, we return to working with the geometry of triangles, which is exactly what trigonometry is meant for. In problem 38, we are given an angle theta between 0 and pi by 2, which has tan of theta equal to the square root of 8, and we're asked to find cosecant of theta. Let's draw out a right triangle with angle theta. We know that tan of theta is the square root of 8. If we were to make the hypotenuse length 1, then it'll take some work to find the opposite and adjacent side lengths that give this ratio. Instead, let's make the adjacent side length 1, and the opposite side length square root of 8. This is a triangle which has tan of theta equal to the opposite over the adjacent, which is the square root of 8 over 1, or just square root of 8, like we wanted. Using the Pythagorean Theorem, we can now find the length of the hypotenuse. The hypotenuse of this triangle has length the square root of 1 squared plus square root of 8 squared, which is the square root of 9, or 3. We'd like to find cosecant of theta, so let's find sine of theta first. Sine of theta is the opposite side length over the length of the hypotenuse, or square root of 8 over 3. Thus cosecant of theta, which is 1 over sine of theta, is 3 over the square root of 8. In this way, we've worked our way around the triangle to go from one trig ratio to another. We are asked to find the side length C given the angles below and the length of the base of the left triangle. Let's label this vertical line with length B. Since tan of pi by 3 is the length of the opposite side over the adjacent, we have that b over 5 is equal to tan of pi by 3. Thus b is equal to 5 times tan of pi by 3. We could plug in the exact value for tan of pi by 3, but let's wait. In the right triangle, we see that sine relates the angle of pi by 4 to the opposite side length, which is b, over the hypotenuse, which is c. So sine of pi by 4 is equal to b over c. And so c is equal to b over sine of pi by 4. And substituting in for b, we get that this is equal to 5 times tan of pi by 3, all divided by sine of pi by 4. Now we can expand tan as sine over cosine to get c is equal to 5 times sine of pi by 3 over sine of pi by 4 times cos of pi by 3. We know that sine of pi by 4 is equal to 1 over the square root of 2, and sine of pi by 3 is equal to the square root of 3 over 2. Multiplying this all out, we get 5 times the square root of 3 over 2 times the square root of 2 times 2. This equals 5 times the square root of 6.